This conference will now be
speak to the
recorded.
audience of MBM Jodhpur. Is it okay? Audio part is fine, Kalaji?
It is fine, sir.
Am I audible?
Yes, yes, sir.
Great.
All is
So
well.
thank you all, and thanks for the very good. So to the funding agency, to the MBM, administration, everybody for organizing this particular FDP. And when I saw the contents of the title of the FDP, like 3D basics and applications, 3D printing basics and application, which is the title. So I thought that let me also have some, if I'm given an entry level topic, I mean, in the first 2 days, let me talk about the basics, the fundamentals of this very important technology, additive manufacturing or printing, whatever we are saying these days, with some biomedical domain cases, right? So let's see, we'll be following this flow for this particular presentation in next 1.5 hours. When we talk about the first group, it will be like more like a basics, or we call it as status of the 3D printing technology. So this status means what is happening as on date, what are the evaluations, how things are evolved, and those things are like we will talk about. And then we will talk about some cases, particularly in biomedical cases, and that's all. So as Dr. Kela said, uh, you please put your questions here in the chat box. I'm able to see the chat. So let's start this Tuesday morning first session. Thanks for giving me the first session, because teachers like this early morning classes. So very good. So I would start with a question and very lighter note. Say for example, we started calling these days this technology called additive manufacturing, and but this is in the domain of academics and industry level. Those who are into it, its public name is like 3D printing, right? So will anybody tell me when this technology was initially developed? Maybe what may be the year, or what may be the decade we would like to estimate? So I know that you are listening. Anybody? So in place of this good morning, let's say Sweta Madam, Swapna Pillai, Pramod Kumarji, when you think was this additive manufacturing or 3D printing technology was initially developed? That's the question. Is it okay? So will you please put in 80? Very good. Pramod Kumarji is saying 1980. Anyone else? 84 to 88. Okay. That is very good reply from Urjita ji. She's saying from 88 to 84 to 88, the invention of stereolithography, that is in one of the technologies he or he is talking about. 80s, very good. So that means three things have come up right now. That means this additive manufacturing is not a one technology. It is like an umbrella of technologies. Number one. Number two, it is not developed mostly by academicians or only core researchers. It has evolved mostly from industry. Okay. So we'll talk about its evolution. We'll talk about some terminologies. We'll talk about the technology impacting the industry. I suppose many of you are mechanical engineers. So I keep telling to my class these days, whenever I happen to the class and they are getting placements in automobile companies, I keep telling it is not going to remain same in times to come. Even the small development like electric vehicles can change the scenario for mechanical engineers, because most of your IC engine gone, lots of casting industry gone. So many things will be happening. Very uncertain future will be there. So in those terms, we'll also talk about how it is going to impact the industry, what are the possible classifications of these technologies and few applications, some relevant applications, how we can relate, and some sort of hardware and software which are there as on date in industry. So it is going to be a very basic talk, as well as it is going to be a very contemporary in the terms of what is happening as on date. Okay, particularly to the academic level which has come up. so that we can use this technology, do research, and tell our students to go for it. So this is one particular slide which talks about these two terms, the difference between subtractive and additive. Say we all know what is subtractive, we all know what is additive. Subtractive means a minus b, and additive means a plus b, right? So what is subtractive? Subtractive is, see, you take a blank, remove unwanted material, so make a plus b, a minus b, sorry, and it becomes a subtractive. So what is a is the blank, b is the product, and when you do get your unwanted, scrap out the unwanted material, whatever material MR process we have. What are the basic MR processes, material removal processes? We already know. You can remove the material by three different ways. What are the three different ways? One could be machining by cutting, second could be machining by abrasion, like all grinding. Cutting is all like lathe and milling. So machining by grinding is going to be machining by abrasion. And then even advanced manufacturing, advanced machining process, advanced material removal process, we call them as erosion process. We go like laser, electrodesage, plasma, electron beam, ultrasonics. They are erosive, or water jet or AWJ. So that is nothing but your A minus B. A minus B itself is a very big world, and you have lots of technologies within this, and many of them are advancing very fast. But the world is A minus B. Okay, well, that is subtractive manufacturing. On the other hand, there is another philosophy, and which is started to be called as additive manufacturing. So what you have maybe raw material, maybe in the powder form, maybe in liquid form, maybe in any other form, blank form, sheet form, and now you add it layer by layer. So what you have, A plus B. A plus B is going to be your additive manufacturing. So you get your product, same product like this. There is hardly a waste here. There was lots of waste because you removed this unwanted material from this blank, so there was more waste. Here it is less waste, and there are so many advantage, disadvantage, we'll talk later, but this is a big difference. Now, can anybody tell me, one is additive, second is subtractive? Can you call it zero manufacturing process? Anybody? Can you put anything like zero manufacturing process? Pankaj Sharma ji and others, let's interact because it's a class, and I also know that I'm talking to people here sitting. Can you appreciate anything like zero manufacturing process? Additive is A plus B, subtractive is A minus B. Can you name something as zero manufacturing process? Plus, minus, and zero also. Casting, okay, very good. And when forming, very good, Pramodji. So I am talking to very learned audience here. So if you are philosophically talking, that was my additive. Subtractive, then forming could be whereby you just use some compressive forces or some normal stresses, and you get your product formed. Maybe you use a rolling machine, maybe you use a press, but that is a zero manufacturing process. Same thing is casting, right? You can relatively call it. You don't conflict with me that there is a wastage in casting also, but yeah, well, that can be again melted into use. So you can relate it. Okay, very good. So we just move on. Now let us see the evolution of this process. What is the evolution of this process? Which process? Some of that in 1770 was some of you already said one word, that was miniaturization. So if you people talk about these days I 4.0, industry 4.0. So industry 4.0 is the term which is used for contemporary time. But do you know what was 1.0, 1.0, 1.0? What was 2.0? What was 3.0? Anybody? 1.0 was in which year? In early 70s. Then when the mechanization happens, so it was from this manpower or horsepower to we moved to mechanical power, and that was like James Watt's steam engine. So 1700, early 1700 was industry. I think Hindi mein we call it Audyogik Kranti. You know with Audyogik Kranti. So early mid 70s. That was I 1.0. Industry 1.0. Industry 1.0. Okay. Then comes the Industry 2.0. When was the 2.0? This was early 19th or late 18th century. Say let's correct century or 1900. So before the World War or so. So what which was used? So was the earlier case, it was like coal, which was, if you have a car, if you want to drive in a mechanical car, you have to keep the coal inside the car, burn the coal, and then let the car move. Or not only the car, in any kind of device. So what Faraday did in 1800, the Faraday's law of electricity came up, and we now started having coal burned and electricity produced. So that was the world. So just early stage of 1900 and late stage was like Industry 2.0. So all the coal was kept away from the city, burn it there, convert it to electricity, send the electricity into city, and then you ask all kind of appliances for within the city. So that was Industry 2.0. Then came the third industrial revolution, or Industry 3.0. That was in 1950 or so, when the semiconductor world came, 1950 onwards, 6 onwards. So that when the semiconductor came, first semiconductor, and then of course the CNC machines, electronic devices, that was your computer came in, and laser machines and conventional robotics and Cad modeling, and of course when we talk about the 1980s, it was additive manufacturing. So additive manufacturing is not this RP and RT is nothing but what? RP and RT. Anybody would like to hear anything about RP and RT? RP and RT. Pankaj Sharma ji, Pramod Kumar. So it is like rapid prototyping and rapid tooling. So these are technologies which are same technologies which is being referred these days as additive manufacturing. But ये ठीक वैसे है जैसे मान लिया एक एक्टर का बचपन का नाम है, तो अगर मैं क्लास में पूछता हूँ कि चलो अमिताभ बच्चन का मूवी में बचपन का नाम ऐसे कोई जैसे डब्बू शब्बू ऐसे ही नाम हो जाएगा, चिंटू छोटू, बड़ा हो कि उसका नाम बड़ा हो गया ऐसे मास्टर दीनानाथ चौहान समथिंग. So modern day name is additive manufacturing, but the childhood name of this technology could be RP, RT. RP is rapid prototyping and RT is rapid tooling. Please do understand this is essential in terms of understanding the principles of this particular technology. Let's just quickly move on to the third, and move on to the third. Now let us understanding this, what is RT. Anybody would like to talk about this RT word, the word tool? Can you name what a tool might be? What a tool might be with respect to rapid tooling? What a tool is? Anybody? Anyone? What is tool in terms of rapid tooling? So let me say, those who are engineering here, or those who are even any graduate, engineering graduate, will tell that initially when we do, say for example, a pattern is made in casting. So say for example, you want a product like this. This product needs to be manufactured out of metal, say. So before you actually make it out of metal, you make it out of thermocol or plastic or anything. Bury into sand, make a cavity, and take it out, and then pour molten metal into it. That's the principle of casting. So this pattern, which was made out of not metal but something, a very easy material, let me call it. So that is a tool. So rapid tooling is nothing but this pattern. So that is with respect to this pattern we are talking about. Okay. There are so many other tools also we can talk about in industry. We have something known as tool rooms. The first products are made, and similarly, whenever you design a new product, the first product referred is as prototype. So whenever you want to launch a product, you have to first do prototyping of. So can you rapidly prototype it? So additive manufacturing technologies came up, or 3D printing technologies came up for prototyping. repetitive prototyping. That's why their names are rapidly. Prototyping, RT and RT, rapid prototype and rapid tooling manufacturing. So let us understand this difference. Now, similarly, what is this 3D also? We'll talk about it. So there are lots of terminologies which are used with respect to this additive manufacturing. One is if I use the word additive along with manufacturing, ALM would be additive manufacturing. So with the, it could be, people also say additive layer manufacturing, ALM also. The use of additive is two terms. Similarly, third term here is the additive digital manufacturing, CAD model, because here CAD model is essential for the digital word is CAD. Anything is made by additive manufacturing or 3D printing. Digital mock-up. People also say the word digital mock-up. The first model, CAD model, or you usually make it on computer, that is okay. Then you do it simulation and various aspects is digital mock-up. Similarly, if you use the word layer, you can call it layer-based manufacturing. It could be layer-oriented manufacturing. It could be layer manufacturing, because you know it's A plus B. So layer by layer manufacturing or layer-oriented or layer-based manufacturing most of the time. So you call it, these are the different terms used. Similarly, if you use the word rapid, you can call it rapid art technologies, or you can call it prototype technologies, RPT, or rapid tooling technology, rapid manufacturing. You can quickly do it. Word to look for the older time or the initial product launch time. If you cycle time is to be 6 months. Every time a new model comes, it will take 9 months. For look at 2-3 years for that. The whole stuff to come out. These days, every second week you find a new launch. This story we had a new Creta model. Now again, I just saw a week back that Creta is coming. This Hyundai is coming with the new Creta model, right? So the launch time is minimized. The new prototypes are coming up very fast. Similarly, if you just look at the digital fabrication or digital mock-up, these are the words with which digital word used. Similarly, if you use something known as 3D, because this is interesting, this is more like common to the public, right? So it's anybody's guess. Say it is more like, say for example, it is one of the technology of additive manufacturing. So we all know, if I'm writing it is x-axis and y-axis, right? X-axis and y-axis. If I'm writing it on piece of paper, this is 2D writing. But if I can get my z-axis, third axis, it is in, I can do any kind of growth in third axis, z-axis. So it is 3D printing, or 2D printing is on paper, 3D printing is there. You can get the third axis, and this is what, though it was one of the technologies of Jet Corporation, which was, they massively publicized, lots of articles came up. So particularly this technology started being called as 3D printing. Okay, so direct, if you use the word direct, it could be direct manufacturing or direct tooling. So lots of words. I hope we simplified those words for you. Any question anybody has up to now? So pretty simple, but we are trying to holistically move on. Now we want to understand the philosophy of this AM. So I'll be now only calling it AM, additive manufacturing. How this AM is going to affect the industry, how it is going to change the world scenario, that is important. So I will like to tell you with respect to this particular example. Now look at this. This is a bracket, maybe in an aircraft which is to be fitted in aircraft. Even if you will see that on the floor kind of brackets are there where the seats aircraft, any of the aircraft seats are mounted. There are holes only. On these holes, these brackets are mounted, and on these brackets, aircraft seats are mounted. So you see that some of the aircrafts will have some partly, economy class, and but modern day these low cost economical aircrafts will have all economical seats. So it can be done in a very quick. So those modularities there. So this is a typical bracket which is required. It has some volume, say 12 to this much volume may be there. Its material could be say aluminum. Its weight is say 330 grams. Now, if you just see it, you understand, you do CAE of it. We can do it computer aided engineering. You will see places where the loads are happening. Say the load is happening where there is a mounting on the bracket. The load is happening where there is a requirement of some kind of arrangement. There is hardly anything which is needed here. But for the case of support system, if you are to make it by A minus B or machining, you need this kind of design. On the other hand, if I optimized or did some CAE, I'll find that this kind of material can be removed. You know, if I have some 50 brackets in my aircraft and every bracket costs me 330 grams, I can reduce 100 gram for each bracket. I can make it 220 grams, say 100 gram into 50, how much? Few kgs, and if I can minimize 1 kg weight for an aircraft in a lifetime, said that if I do aircraft, I can save at least few thousand gallons of fuel for that particular aircraft. So you optimize and you can see that this is a new design which is possible. Now this new design is possible well, and how to manufacture it by conventional A plus B, A minus B processes, zero processes, Z processes. There is going to manufacturing, going to be cost effective, less wasteful, so it is going to be sometime rapid manufacturing, which you already seen, and components can be customized. At that, then the development or agile manufacturing is possible. That can reduce the lead and time to market, and it can revolutionize low volume manufacturing, because I need to go for a customized product. Say I have a car which has lots of components. Suddenly I find that one component has gone wrong. I can, if I have the design, I can quickly print and use it, right? Or imagine a case, you have gone to space somewhere in the say space station. Now you need, or maybe in desert you've gone for a picnic in Ladakh for 10 days. Now suddenly your component, somebody has to ferry it from Delhi. What could be possible that if you have those designs which can be sent by mail, and if you have a one printer along with your group and some raw material, you can just print and use it. Okay, so that kind of thing is it, your thought process is the creativity. That's why people say it is going to revolutionize the industry. Now let's understand about this, the generic additive manufacturing sequence covered for you, but let us quickly move on. If it is you are, please do tell me, Pramodji, Swapna, that if it is covered, do tell me so that I can quickly move on to. Okay, these are all generic processes in the sense that this is how things move. So initially you may need to make a CAD model. A CAD model is required. Then once the CAD model is there, you convert this CAD model into a CAD model will have some file format, say based on the kind of software you use, CATIA or PROE or Fusion or Unigraphics, whatever the CAD software is, it will have some file formats. Now convert that file format, save into STL file format. STL file format. What is the STL full form? Anybody would like to write here? STL full form. Anyone? STL full form. So let us that will be interactive for all of us. What is this file format? Anybody? Okay. Then once you have that STL file format, then transfer these files to the printer. So Pramodji has written standard tessellation language, tessellated language. Okay, it's a kind of file format or triangle language. Tessellation का दूसरा नाम है triangle. Very good. Thank you. So those words are there. Now we have this file format. This file format goes to a, is saved with a machine called printer, 3D printer. Printer will have a setup, say for example, these are all the file which was there in CAD model. You have converted into a file format which is STL. Now it is transferred to the printer. Now the printer setup is there, the machine is there. So up to now it is all computer. Now you have to build it. Build it means in CNC machine, turning or milling, what we say, we have to machine it, but we will not call it machine, we call it building, right? So it is a building time. In the way in machining we say MRR, material removal rate. Here it is what? Build time. That means if you have to make a model, a product like this, now how much time is required to build this? that is build time. So you build it. So build is actually the real processing. Anything which is before the build is known as what? Anybody? Anything which is known as before the building, and anything which is after the building. So that is known as pre-processing, PRE, and this is known as processing, right? So post processing is like you may have to remove some kind of uh, added material, this kind of support material, may do some cleaning, may do some kind of embossing on it, casting on it, and get your product ready to use. So what was the philosophy? You are sitting somewhere in Jaisalmer, you don't, or maybe in jungle somewhere, you don't have any cutlery with you. Now you want to have a cup of tea. Maybe you had some other machine for making the tea, or some tub to make the tea. Fire is there. Now you want to this cup, you want to model, design, and quickly print. You can make within say half an hour. Okay, so that would be the philosophy of your AM generating process. So this was the philosophy given by Ian Gibson. I'll use this gentleman's name again and again. Why? Once you understood this, I can now move on. And the next moment comes to the classification. One way of classifying additive manufacturing technologies are based on the type of raw material you are using. So what are the raw material? It could be a solid. The raw material can be raw material, or liquid. It could be a powder raw material. If it is liquid, you can sometimes melt it, or you can polymerize it. If it is simply melting it, which is already a polymer, there could be an important technology and very widely used technology. This is known as FDM, fused deposition modeling. FDM. So what you do in FDM? You have a polymeric wire, extrusion wire, and that is melted and deposited layer by layer. So FDM technology does that. Now on the other hand, what you have? You have monomer plastic. Now you use some kind of source of light or some kind of energy, and you polymerize it while you are getting the shape done. So that could be another liquid based technology. One of the important stereolithography. Other could be polyjet. Poly means multiple jets. So jets are coming and they are also polymerized together. Jets of monomer is coming and polymerized. Then digital light processing, DLP. Again, a new word has come very quickly. Technology and doing wonders. DLP. Similarly, if it is solid, there are limited technology within solid. One of the solid-based technology could be laminated object manufacturing. The whole idea is you stack these sheets layer by layer and get the product shaped. So if you think slide is not changing, okay, that means the network is an issue. Is it still the case? Is it still the case? Anybody please unmute and tell me. Okay, Pramod is showing. So I am trying to talk about this raw material based Pramodji. Okay. So maybe Madam Gaur, you just check it whether with your network may not be that good sometimes. So others are able to see it. Good. Thank you. So let's move forward. Possibly it will come. Now that we have, okay, very good. Thank you, Gaur sir. So now we have this third category called powder based. That means you can have liquid, you can have solid, you can have powder. So powder based, you can either melt the powder and get your product done. So when you melt the powder, there are technologies will be SLS, selective laser sintering, technological laser sintering, or SLM, selective laser melting. Please do. These are the technologies mostly for polymers. Understand which are more polymers, but we are mechanical laser engineers particularly are so selective laser sintering, selective laser melting, direct laser metal sintering, or electron beam melting, or laminated engineering net set, and as lens again coming in a big way. So lens, EVM, direct laser metal sintering, or SLM, or selective laser melting. These are the technologies which are coming. So you need to big way. You need to understand and they are mostly for convert those metal into a powdery form metal based. So those who are good in powder metallurgy, it is now their time. If you understand powders, if you understand the science of powder making, mixing of powders, if your powder metallurgy is good, well, you are well suited for these additive manufacturing technologies. All right. Then the third category within powder. In powder, we have another technology, and one of the technology which came by Jet Corporation was 3D printing. It is very simple. Jet Corporation came up with an idea that you powder, say in 2D printing, say particularly color printer, we have cartridges of different inks. Now, based on the ISKY code of computer, whatever you want to type your name, say for example, you want to type your name as Pramod Kumar on the screen, you type your Pramod Kumar, and then that can be printed on the paper. How it is printed? By simply those the ink is flowing on, ink is spread on the paper. Now, in place of ink, if I replace these cartridges by say powder and glue, powder and glue, powder and glue. So I spray some powder, then spray some glue, spray powder, spray glue. So that is binding, and that is what technology could be 3D printing. It's very simple and understandable by everyone of the technology. It's very simple and understandable. People can started calling this whole technology as 3D printing technology. And philosophically, it is okay also. Why? Because it is a third access you are getting. So 3D printing, third access. There are other technologies called pro metal within this binding, so that comes under this powder metal system. Okay. So anybody has anything which, please do chat, because I just partly opened my chat also parallelly. So I'll be happy to interact and note, because otherwise there is no point. I simply say, and so please keep chatting here, keep putting your questions here. Then if you look at these fundamentals, very good. Sweta madam is saying everything is clear. So I can be a little faster. If you say I can be a little faster. So whole idea is to have these commonly used materials, say for example polymers, plastics, or metals, or others. Based on this as on date we have lots of materials which are, earlier it was only plastics, now metals are being manufactured by them, or other materials like ceramics and photopolymers are also being made by additive manufacturing. So steel, titanium, aluminum, plastic, everything is plastic, may bioplastic composites being manufactured, plastic. So metals, materials, but still, if you look at the market scenario, this is what the ceramics, composites, and the market scenario I want you to understand. See, if you just look at world over, 56% people are presenting photopolymers. Additive manufacturing is photopolymers. 46% are these thermoplastics. That means it is close to 96% that is plastics. So people are still dealing with plastics or plastic-based material by additive manufacturing. Only less than manufacturing, and that too powder-based. Or metal manufacturing. There could be thermoplastic 2%, and other categories of materials like composites or ceramics in one category. Recent data, 2020 data. I hope this makes you sense, because this is the okay. So moving next, now people also create or material removal. So if you are in the tool room world, you understand tool room in the world. Tool rooms are those places in every new thing has to be developed. So if you are a tool room engineer, most respected person in the industry, particularly technically, other than those management people. Okay, in India particularly, tool room are the most recently we started calling it R&D engineers. So they are the most respected, and they are the most I mean knowledgeable and experienced. So if you are a tool engineer point of view, if you look at material remote could be one. If prototyping, it is a material addition could be one. In material addition, you could do all whatever I talked about, like liquid solidification of polymer, or various other phenomena people provide it. So I put this content for you from the particular slide, saying could be by layer SDM technology or to classify it. Similarly, this is the likewise you can also more by different classification we have other than one gentleman called this recently none initially I just talked to you Ian Gibson. He is works in US government. He was the team lead for this he ISO team and he do standards and he has classified all those manufacturing into 7 families technologies which are more than 500 technologies of additive 7 families. So I need your attention over here, very important. Don't worry Prem Shankar ji. So whole idea is what we do is Prem Shankar. Let's go classify these 7 GIs. We classify this and when I talk one students I acronym. So I call them as MV and BSPD. So MVM and BSPD are the terms, the first forms of this is purely polymer families. So MVM, those technologies who can do only and metals. Those technologies who can do this polymer, both they'll be metals, they'll be referred as BSPD. MVM first MVM is BSPD. So MVM refers as when you material, what are the technology? You have your material, use material, which is particularly polymer, which is only suitable for plastics. You do it A plus B product. Make your product A plus A minus. So M is material extrusion. V is polymerization. So there are technologies we have FFF, fused filament deposit fabrication, or FDM, FF and FDM material extrusion. These are all popular case of material technologies I am listing here, and FDM. Similarly, another popular technology is under V, that is wet means एक टैंक होगा जिसमें wet photopolymerization हो जाएगा. That means you will have a tank monomer plastic and then so when you polymerize it, that source of energy can be what is required initially when we talk about STL technology, stereolithography technology, or it could be DLP, digital light processing. So that is also for polymers only. Stereolithography is short form is not STL, SL or SLA. SL or SLA is what is this. Similarly, DL for BM. Third one for material. That was your material polymerization is your material jetting. So your material which will be jetted, it will pass through a jet. A jet, it could be single jet or multi-jet. If it is multi-jet, it is again please do understand it's for polymer only. So one of the technology is doing wonders in this polyjet and multi-jet modeling or continuous inkjet. So but polyjet is quite popular and low cost these days. People are selling extensively selling this material jetting technologies. Okay, so they are all suitable only for polymers, and polymers. So three families talked about: MBM, material extrusion, wet photopolymerization, and material jetting. Then another technology which is more suitable for polymers without doubt as well as metals. So let's call them as BSPD. B stands for binder jetting. So what is binder jetting? Binder jetting is you have to add binder into it. And now within that binder, you get your green briquette, more like powder metallurgy briquette, and then you take it to a furnace and sinter it. So that is binding. people have lots of names. So voxel jet is another technology, 3D printing is another technology, XNet is another technology. Okay, so this is polymer as well as, so B as well as the first B. Binder stands for the third category. Rather, in total, it is the fifth number. What is S? S stands for sheet lamination. So are manufactured that there, like you have a layer of sheets which are like layer placed layer by layer. They are cut by some process and then laminated. So sheet lamination is both for polymers and metal. As all is also sheet lamination metals. And this is classification which has F2792, ASTM F2792. Has come juggernaut. Recently, and this has sold the technologies. Okay. With respect to this, lamination is clear P. This P stands for lamination here. Then we are powder with another component of technology, very important technology. As we have the important technology as the technology as well as selective laser sintering. Laser to a separate sinter by lead to a powder metallurgy. But here the laser you can select it. This is the technology which will be sintering and it is coming a very low power, very fast, low power, and this it is can be done. So but if it is beam of lighting can wonderfully electron, it can very fast metal powder. Okay, beam may do it for metal powder. So this is powder is you just keep on sintering, on protocol imaging, this light source, and your product is made. Well, this is your on technologies SL. So is it my voice? Shall I change the network? Everybody's voice network in the next. If you have issues, everybody has issues, please do tell me. I can move to the next network. And if it is individual problem, please check your network. Okay, my voice, I'll change the network. Is it okay better now? Pramod? Now it is fine. Thank you. So I'll be little louder. So we are talking about MV. So this is your technology, right? V stands for photopolymerization, and these are lots of technologies coming under this family, and lots of products are possible only for polymers. Then is M again. So here what you do, you have this jet of different materials, which is again, you know, polyjet. So multiple jet, polytechnic type. So you have this, which is used for making mainly for, say, one of the technologies, polyjet, particularly making scaffold in biomedical devices and all, is extensively used. So you use the light source can be used in the form of ultraviolet lights or any other light source. So you can call it metal jetting, but only limited to polymers. Okay. Fourth is BSPD, so binder jetting. This is what you get your product like this. Lots of powder metallurgical product, but they have to be sintered separately. The only difference is in powder metallurgy, we are limited by the shape of the product because we have to limit the die shape. But here you can have unique product, and these products are made by this binder jetting, 3D printing category. So one of the binder jetting technology is 3D printing. Okay, but you can make unique product, good products, and then they are green briquettes and take it to sintering process, so they can be sintered together similar to powder metallurgy. So those people who are limit in powder metallurgist, now they started making lots of complex parts using this technology. As lamination, you can have any kind of ceramic part. You have layer by layer machining. So what you have this, this is your one spool. The seat is coming like this. Now the seat is continuously fed. Now you can cut it by this electric mirror or something, and then cut open and just laminate one over the other, and the shape of the product like this is obtained. So this is sheet lamination. It could be both for polymer as well as metals, but it is extensively used for composite materials. Lots of products can be made by composite materials. So laminate technology has laminate making. FRP laminate making is one technology. You already know there are hand layup and those technologies. Now those technologies are this is being added with those. So VRTM, VARTM, vacuum assisted resin transfer molding. Those technologies are there. Now with the advent of sheet lamination, people are making laminates by this, and then too complex laminates can be made by this process. Okay, so it has affected many spheres. P is the powder bed diffusion. As I told, lots of products have come up by this family of products, and one of them is SLS, selective laser sintering. All right, selective laser sintering products are there. So idea is you have your powder which is coming up like this, and then wherever the powder is spread over here, wherever the powder is sintered by laser, is bonded with the workpiece, with the build with the metal, with the base material, and then other powder is taken back, sucked back, and again filled and utilized powder. Okay, so that is your BSPD. Then comes D, that energy deposition or less kind of technologies. So this is extensively, I know it's a welder's domain. So I remember if you have to do some kind of repairing work, you can use DED. Earlier also we have seen lots of this aviation people using DED. They will do welding on this kind of turbine blades and then they do the grinding. But now you don't have to do the grinding. You can precisely do the deposition, and this is DED is doing. So I remember we in one of the bases, the base repair depots of aviation sector, we were like these helicopter shafts were getting wear out over a period of time. Then we have to build it by some welding deposition and then do the grinding. But here it is not required. So DED is doing wonders with respect to this kind of work. And DED is a family. One of the technologies lens. There are so many other technologies which are there which are not covered here. So as far as these 7 families are concerned, we have talked about, but families are covered. What is important is the software part. So let us quickly look at the slide for CAD modeling software. So which are those software? I think you know it. Just Google it. You'll find lots of softwares, but I have listed them. I have listed them in 2 categories. One is proprietary software. Second are open source software. So what are open software? Open source, which are freely available. You can download like FreeCAD, TinkerCAD, Open or SCAD, or Rhino or Blue. They are all the softwares which are freely available. You can model anything. Similarly, if you look for the proprietary software like CATIA, Creo, which is from PTC, earlier was Pro Engineer, Inventor from Fusion. Again, it is free for academicians for 4 years. Fusion 360, again from Autodesk, which is free. Dassault Systems, who owns CATIA, has procured SolidWorks also 5 years back. Solid from Siemens, they call it a product lifecycle management software, and NX Unigraphics again from Siemens. So there are a couple of lots of acquisitions have taken place, and now big companies are like Autodesk, PTC, Siemens, and even software called Mesh Mixer again from Autodesk is again doing lots of work is required. So what we have listed here is this software and their use, because this is a prerequisite. Without software, there is no additive manufacturing. So CAD modeling softwares are done, but CAD is not sufficient. What we have to do, we have to convert this CAD software into slicing software for XML file. So you need to have best quality slicing. The slicing can be again done by some open source or some paid or freemium. This term I got from a student only. What is freemium? I asking, sir. Initially they are free for some level, and then you can graduate to premium level. So that those are nothing but freemium. Okay. So these are softwares referred as. I use my in lab slicer software. I also use Cura in one of the uh, free open source software in one of the printer. So likewise, you can do this slicing. The list you can identify useful, and we can share also. Okay. Then coming to another important part, it is not that everything you have to make by sketch only, like in CAD modeling. What has changes again is it is not that CAD CAM only have, it is scanned. First you can scan something, and scan and then convert that scanned file into a CAD file. So there are lots of hardwares coming in the form of 3D scanners. Okay, so 3D scanners again are softwares which are responsible for to be used with this kind of devices, scanner devices. Okay, so there are scanner software which will be responsible. There could be mobile app based, your mobile based, or they could be your computer based, desktop application based. Whatever scanner you are buying, usually you'll get to buy a software or use a free one. Okay, so this is because this data can be extensively used here in the models. So you can very quickly scan purpose. CAD scan and then do little bit of formatting here and then print it, slice and print it. So lots of software skills are needed. Then of course the print machines, the one which are responsible for the actual realization of the product. So so many companies. So I listed 2 categories, not limited to that they are the only one, but some sort of work like Stratasys is popular, 3D Systems, HP, Formlabs, Ultimaker, Carbon, Markforce, EOS, Nanoscribe, Workslate. Okay, so lots of companies under in the world premier companies in manufacturing of 3D printing. Similarly, the lots of Indian companies have come up in terms of these low cost, particularly polymer based printing. So I have a student of mine who manufactured in Jaipur only the AHA 3D. Similarly, company which is doing wonders in India is like Think 3D or Nova Beans. They're all imagery in Mumbai. They are 3D Bazaar. So they support any kind of fabrication. You send them to the design, they will print and courier you by Amazon or whatever your favorite, Flipkart and others. So this is the world happening. So that was hardware. Similarly, you also have to understand that popular scanning tools, scanning hardware. So we talked about one hardware is the printer, second hardware is the scanner. So scanner also are coming by companies, right? Many of them are Chinese, unfortunately, but we can buy some good European companies also. Scanners from the Einscan or ScanJet or GoScan. There are various companies, or one low-cost company called Peel 3D or Revox 3D Print. So they're all scanners. So even medical people are using extensively the scanners. Artists or archaeologists are using extensively the scanners, and then they modify it and print it. Okay, so this is the world of this is what we are talking about now, the basics of additive manufacturing. Anybody has any question before we move on to this biomedical domain, which is again an interesting case studies and lots of work. Let's quickly. I want to hear at least 2% offline or audio, and any question if you have, please do come forward. Up to now, anyone, or put in a chat box.
Sir, good morning.
Yeah, go ahead, sir.
Sir, I would like to ask you, sir, if we want to scan a composite, sir, so is it possible via scanner?
So composite product.
Yes, sir.
Product made
If
by
we want to
composite,
scan a
you say?
composite, yes, sir. I mean multi-material product, then is it possible to scan it via a scanner?
Yeah, it is possible, sir. Whenever whatever scanner knowledge I have based on this, the one limitation with the scanners is the reflectivity of the light. If you have a material which is highly reflective, then it will be a difficult thing. So there are some powders which come along with your scanner. So just spray those powders on it, and then you try to scan it. Should not be a problem until unless the reflectivity is an issue, because this captures only the contours and the shape, not only the integral material of the. It won't give you the internal material properties that you have to integrate into your CAD model. So it can be scanned. You can scan clay model, you can scan composite material also, as long as they are not reflective. Answered, sir?
Right, sir. Thank you, sir. Thank you so much, sir.
Then the next question is from Pramod Kumarji. And any follow-up question from you?
No, sir.
Okay. So Mr. Fosdar is asking, sir, what are the opportunities for research in this area? Well, there are. It depends upon what level of research you are looking for. Say, for example, we have an extensive work in my lab was on finishing solutions. So we have a technology called abrasive flow finishing, AFM. So what the scholars have done, and I also do some composite material, which is a funded project by DRDO, and I'll quickly talk about. So what we have done, we are trying to do some composite laminate manufacturing by this additive manufacturing processes. Now we have this AFM technology which has matured. We have our own patents, technology transferred. So what we do, this problem, there is a post processing required. What is the post processing? Post processing is like you have this layer by layer machining. Layer by layer products are there. So this surface is not that good. Sometimes you need a very good surface. So can we use this AFM technology, which is mainly meant for finishing complicated parts with complicated surfaces? So that so we are trying to integrate this AFM and additive manufacturing. So there are so many metal-based manufacturing. If you are from welding domain, related to welding technology, there are lots of research areas. If, as I told, if you are from a powder metallurgy domain, well, within the powder metallurgy, there are so many integrated. So there are so many research areas within the software, optimization related. Many things are there. So it's totally up to what is your background and where it fits in. Other than that, well, there are lots of case studies. You can, as I talk about this case study, additive manufacturing of Jaipur food, there are lots of based research you can do, because application based research, in the sense, it is like when I was graduating in what was the people were moving from metal to plastic. So I was told that many people in Mumbai are, say, for example, a scooter which will have all 80% parts of plastic and 80% parts, 70% parts are, say, metal these days. But when 90s it was only 5% parts were plastic. So people have replaced those plastic metal parts with plastic parts. Similarly, now you can have lots of application bases that you can use parts which are non-manufactured, non-optimized, and you can replace them by AM parts. So I hope I answered your question, Ozar sir. Okay, so let's move on to the next one. And the next, let's talk about these quick technologies. Whatever I've spoken, we have used in a lot, not only in biomedical domain, but so many domains we are working in, particular dimensions we are working in. But I just thought that I can cover only one case study in next 20 minutes, so we'll talk about it. Okay, so there is a question from whether we can print parts like combination of spine and ribs, where the spine is composed of PLA and ribs for TPU. Yes, it is possible, but they are all. Please do understand, these PLA and TPU parts are not biodegradable. I mean, not biocompatible, particularly. So you talk to the surgeons before you actually think like this. So as far as model is concerned, well, you can guess. So I think Ms. Raj or Mr. Raj, sorry, I don't know. Uh, I won't be able to give you the right salutation to you, but please do understand. Let's understand this biomedical device with respect to your query. So look at these biomedical devices. They are extensively being utilized. Now look at this. There are devices which are like implants or used in our implants or human body. Not only this, so people have classified these biomedical devices whether they are low risk or high risk. If it is medium, class B, much more higher, C, and highest risk, class D. So if it is an implant job usually fitted in somebody's ankle, a ankle joint, or if it is a stent inside the arteries, then it is a class D implant. On the other hand, something like assistive devices, polio caliper, diagnostic equipments, monitoring equipment, they will be therapeutic equipments. And there are other equipments like orthotics. Orthotics are those assistive devices, and prosthetics are those like artificial limb or artificial hand, or like they will be prosthetics. Whereas surgical tools, implants are high risk. So it is up to us where in which domain we want to work. But there are lots of people have used extensively additive manufacturing in this biomedical device domain, and this is one area where it has revolutionized. So even if you look at global market device, market, see, this is 50% is diagnosis and monitoring, then therapeutic, as I told, assistive devices, then surgical, again this yellow color, red color is others. So there is a big market. And I recently talking to somebody, and I just came to know that in US and Europe, healthcare is number one employer. Number one employer in US and Europe is healthcare. In India also we'll have though young population right now, but next 10 years we'll have some aged people. So healthcare will be employing lots of people. Technology will be needed for healthcare. Okay, so we'll talk about this aerospace domain on big structures that can be printed. Okay, so we'll talk about this combination, whether the PLA and TPU together can be printed. Yes, they can be. They can be if you can have multi-jet, and even by FDM also you can do it. And then of course the flexibility has to be studied in advance in terms of GCE part. Right, Raj sir? चलिए आगे चलते हैं. Let's move next. So that was your biomedical devices. Now let's move on to one case. One case where I am right now in Jaipur, and whenever I go to any out of India, and if I say I introduce myself, I am from Jaipur, people say, "Oh, Jaipur food," particularly those people who are academics world or in kind of biomedical world, right? So low prosthesis limb, which was developed by Dr. PK. Jaipur foot was a low cost which was developed by city in late 70s. So this was an improvement over the earlier Sage foot, which was a European development. Sage is a wooden foot, solid ankle cushion heel, they called it. What he has done, Sage was costly and it was not fitting to Indian environment. So Dr. Sethi came up with a foot like Jaipur foot, and it was considered by the Times magazine the greatest inventions of the 20th century. How? Because in that time there were lots of products which were needed, and Dr. Sethi used it very fantastically. That he used the local manpower, used the locally available raw material. So you just recollect, in 70s you were using all kind of chappals were made out of this MCR, microcellular rubber. So he used the same rubber he used. So he used rubber for more this making this solid ankle block, this 4-foot block, these towers, and then even steel rod. He used wood and then wrapped around this tire cord around this one, and then the skin colored rubber, and everything was cured in a furnace. So that was the idea, and that was the design of Jaipur food 50 years back. Okay, so this is what manufacturing here. It's conventionally manufactured, multiple materials, as somebody said, combination of materials. What is the combination here? Because you need flexibility more, you need rigidity more here, you need reasonable flexibility here, you need to hold it somewhere by ankle, you need a, lots of strength at the heel level. So that is what is wood, and wood is also layered. Okay, so imagine as a mechanical engineer or as a design engineer right now, what a doctor in 50 years back, doctor from SMS hospital, he thought, he worked on, conceptualized, and developed this product. Okay, and that was so useful to the people, common people. So that was idea of Jaipur foot in 1968. So one can walk, cross leg, sit, and squat. Cross leg बैठते हैं ना, मंदिर में बैठते हैं वैसे. So likewise, he came up with an idea and he used this local available material. So there are two designs, one with gold, one without gold, and these are the foods available. But what has happened in last 50 years? Sorry, what has happened? One problem with this design was this was not patented. No one was the owner. Everybody across the world, they started making their food. They started calling it Madras food, Nisa food, Ram food, Sham food, and they started making it, non following the standard manufacturing practice also. This led to the degradation of this design, and there were lots of failures. We did a research paper, a study in Fdm Jaipur, that was in 2017, 16-17. We call it epidemiological study of this Jaipur foods failure, and we found that what are the reasons, those flowcharts. I can share this research paper with all of you. And then we also came out with an idea that why people were amputated, what was the reason in it. Traffic accident, which was maximum, the railway accident, and then like the sugar problem to the people, and lot cancerous people issues, infections. These were the reasons for the amputation, and they use this, and why it failed, we wanted to know. So when the failure regions were identified, they try to identify which are the failure junctions. So if you have seen this design, these are the design. These are all CAD model parts we have done it in that. Just to explain, I am trying to show you. When I look at this, I see that which are the places which is failing. The failure regions. So maximum failure is happening at the heel junctions. Okay, and then another study also came out that in Indians it is the trauma which is 87%, out of which 69% is the traffic accident. On the other than the Western world, trauma is only 6%, right? Whereas 47% of the is like the whereas the reason is 47% failure is because of this heel block. Okay, if you have to dig it, people were manufacturing. So now moving next, manufacturing it in a art mode. This bag initially controlled, but now it is because of the cost, because now we are footwear from MCR to now what is our chappals and shoes are made out of. The sole is made out of anybody, which material? the soul of your shoe these days. It is polyurethane or EVA. So the low cost MCR is not there. It is still in artisan mode. The manufacturing is non-standardized, but those people are not interested. Those artisans are not there because they can't afford this kind of day's salary. Okay, so can we have some kind of contemporary manufacturing with this technology? Can we have this kind of like enhance the quality of it, or can we manage it? So based on this thought process, some work were done. One work was this study on, then use simple industrial engineering concept, gauge development, fixture development, so that this manufacturing product can be enhanced by the artisans. The third one is we assess the compressive and the tensile mechanical properties of this Jaipur food material as it is. Then of course we did the CAD and CAE and did lots of additive manufacturing plant. So was the standardization and these contemporary technologies were identified. Finally, manufacturing standardization by additive manufacturing was initiated, which is still in work in progress. So as Mr. Raj told me that what are the areas, these could be the areas. Okay. So, and one product, this is the way somebody manufactures Jaipur food. So what we gave them some kind of stencils like this. So the life is easy and it is much more standardization so that the failure is minimized. So lots of stencils were made and printed by additive manufacturing. These stencils were printed by FDM technology. So lots of 3D printed parts, or if you want more, you can make it out. Sheet metal working aluminum can be used for the sheet. Okay, based on the size of the foot, 4 by 1, 6, 7, 8. So all industrial engineering concepts we use. And the prototypes were tested, and of course, without doubt, it went very well, and the study was successful. And they have started using, the artisans have started using it. Another thing is we wanted to know the exact property of the material which were planned by Dr. Say Jaipur food processes. So what was the wood? He used this cheat wood and Ardu wood, and we wanted to know what is by using the STM, Instron UTM, what are the properties of that particular material. Similarly, microcellular rubber. EVA also we wanted to know parallelly. Skin color, what are the properties? Tire board, steel board, those properties were identified. So once those properties were identified, the next step was to, from this artisan way to CAD/CAM model. Once this CAD/CAM is there, you have some kind of standardization part, and then you put the material properties into it, parts which can be standardized, and then we try to additively manufacture. Our prototype was manufactured, and then of course clinical studies were. So could you appreciate this flow chart? So this is under the heading of CAD/CAM or CAD/CAE of this. So what was the idea? First, you have to do the CAD modeling. So CAD model these parts separately. We use this fusion tool for modeling this. So these parts were separated. Then they were assembled. Please do understand, it took lots of time to model this kind of organic. I'll call it organic product. ORGANIC. Organic product. Why? Because you just see the shape is not like standard mechanical product. Okay, once you have that, it was taken for CAE, but before CAE was done, we need the properties of this. So property of this block, properties of this block, and then forces were static studies were done. Okay, so when you do the CAE part of it, static study part of this, you read the material properties, and then you can get the outcome. So you can get the displacement, where it is coming, so that you can estimate the failure. Okay, this part is done. So it is again all linked up. Though it is additive manufacturing, but without additive manufacturing, without this CAD and CAE, there is no additive manufacturing. Without this, let's see, material properties, there is no additive manufacturing. Okay, then this is the final print which is coming out, but it is still, I'll say, it's non-functional. Why? Because it is not functional. Because it is made out of a non-functional material like ABS, simply printed just to verify the design. Cross sections were printed out of different material, and this is what I'm trying to say. Then of course we wanted to replace this APD. So somebody has started the mic. So please unmute it. Please mute it. Or you have to ask something. Venkatesh Yadav ji. Venkatesh Yadav. If you have to ask, else mute it, please. Organizers, if you can mute him. Thank you. So here we are. What we are trying to do over here is we are trying to model this and do additive manufacturing. Now let us move to functionality part. So functionality part, a new material like PTU. This TPU. What is TPU? Thermoplastic polyurethane. Again used. Polyurethane is PU is used in our footwear. जूते में आता है काम. आप जूते का सोल PU का बना होता है. So PU का एक category thermoplastic TPU thermoplastic, which is a printable category, was again tested for these properties, and we use TPU with levels of films, they say from 10 to 100%, just to identify whether it is suitable for this kind of product like foot. Right? So its hardness was tested, is compared with MCR, various grades of TPU, various grades of it was tested with wood. So that was the trick of the trade, and it tested when it was printed, tested using a standard technique. How much is the heel angle? How much is the percentage of failure is happening? What is the compression? So if compression is greater than 5 mm, well, the feed is, if it is showing more than 5 mm, it is a failure category as per ISO 10328. So the failure here was less than that. Therefore, TPU 40% kill, and the weight of the foot was coming at 315 grams. So this was the last one. Still, one Amtech scholar is working on it, and we are still looking for good researchers to work with, because actual product is like this with various compositions. And of course, we have to test it. Lots of things, lots of testing has to happen. Clinical trials. So this is what we talked about this case study, and I hope this part is understood. If you have any quick question, you can ask, please. Anybody? Anybody has any question? You can unmute and ask. Okay, so you can even chat right here in the chat box, so I can answer. Meantime, I would like to tell you about this advanced manufacturing and mechatronics lab here in MNIT, in my lab. So what I have these old CNC machines that have been retrofitted. The vertical machining centers and turning centers and EDMs and CNC milling, all those things are one bread and butter, particularly for my basic research in manufacturing. And then there are other micro machines like this DT110 hybrid micro machine, which is for many size micro machining, which is again used. Third group of machines that I'd like to tell you about this advanced finishing solutions. We call it AFM, abrasive flow machining process. So this is a commercial machine to AFM. Lots of product development happens through this. So because we wanted to have our own machines, so we developed this low cost one-way AFM. And for doing this, we did lots of additive manufacturing. This low cost additive manufacturing machine, which itself was part were machined here in my lab by Akash of R3D. And then here also we attempted helping him for finishing this nozzle of this particular machine. So it is like one helping other. Since this machine requires your cutting tool is nothing but a viscoelastic fluid, so a rheometer is there so that we can assess the rheology of that particular fluid where it is used in this particular finishing solutions. So somebody asked the research level. This is one possibility of research. Okay. Next, of course, measurement. So there is lots of electronics required. So we have this basic mechatronics kits for DSO, PLC sensors, so that any of the machine which is needs to be automated can be modified with. We also have certain high-end tools like this 3D profilometer. Whatever mini-size product we make, we can see it through this. Of course, rheometry and weighing balances and dynamometer is again for machinability study. Roughness profilometer. Similarly, lots of tools in terms of software like LabVIEW for data acquisition, Fusion, again for CAD CAE, CAD CAE. We also have this from Altair for all kind of little bit of advanced studies. Of course, multiphysics for some kind of research in material properties. Then these are a couple of projects which are currently on. This one is like we are doing a product development for newborn babies born with twisted legs like this. So we are trying to develop an orthosis, print it, use it extensively, and it is going in clinical trials so that this kind of plastering can be avoided. This is a torturous to the babies, right? So this project is still on in my lab. I'm looking for some good scholar for that. Similarly, one DRDO project so that we can make these hybrid laminates, carbon Kevlar laminates, do their modeling, do their testing, support defense industry in this regard. So this is a typical vacuum assisted resin transfer modeling setup. Then another micro domain based fabrication and finishing product like mini size products based on heat reaction supported by DST SCRB. Okay, so these are all of course since I talked to you about the processes and orthosis, so this is the research group. Scholar Siddharth has graduated, but some series still there. Abdul is doing in the additive and thing. These two are scholars and students who are still working. He has graduated. Praveen has graduated. Samit is working, and they all have graduated. So a bit of sketches I use from the literature. So these are the references, and this is my team. Thank you very much. I'm still open for the questions. Please come forward.
Sir,
Yeah, yeah.
sir, is there any specific type of meshing that we have to perform while analyzing these additive manufacturing components in these softwares like
So you are talking about messing because I just missed your word. Mess. MESS, right? Or you're talking about machines. Please come again with your question.
Yes, sir, I was asking, is there any type of meshing, particular meshing that we have to perform while analyzing the additive manufactured products in the softwares like ANSYS, Hypermesh, Abacus?
Yes. I got your question, sir. Your good name?
Sir, Parth.
Okay, Parth. Good question. So whenever we do CAE, computer engineering, or let's say FEM, finite element modeling or analysis. So the whole idea is what is the right kind of mesh to be found for what kind of product. So it is not related to the meshing is not related to the additive manufacturing particularly, but what I am interested is the geometry of the part, the material of the part, and the complexity of the part. Based on that component, I have to decide my mesh. So unique to additive manufacturing need not to be yes, but of course geometry of the part and its structural integrity or the requirement of that particular whether you are interested to use that meshing in fatigue or you are interested to use it in any kind of simulation purpose, that time you will have to identify the right kind of mesh. Okay, but AM basic, I need not to say that particularly AM this kind of right mesh is required. Okay, Parth?
Ji, sir. Thank you, sir. Sir, can I ask one more question, sir?
Oh yes,
A
go
bit
ahead, sir.
different. Sir, I read one of your publication in Taylor Francis regarding the machine ANN ANN in tensile performance of PLA. It was a composite, sir. Sir, so can I ask you, sir,
Right.
ki what is the scope of machine learning in additive manufacturing?
See, machine learning is nothing but whatever we are doing. For example, we are doing turning. Let's start with the turning. Let it be additive or milling or whatever it is, non-conventional also. So whatever data you have, say while doing any kind of work, you have some input parameters, you have some output parameters, right? Input and output parameters. Now please do understand, if you have those data which you have been doing since long, so you have those data, so capture those data, use any of the tool like ANN. So what we have used, artificial neural network or fuzzy or any other mix of techniques. So now you have those data with you, you have these techniques with you. Now what you can use, you can use the data for modeling or rather enhancing these particular models which are made in ANN or all those, and then they can predict for you. So that is machine learning. Now, say for example, I have some additive manufacturing if I am doing, and based on the additive manufacturing, I have some input parameters, and I found some parameters. Say the case you referred, which was done by a MTech scholar. So what he has done, he has used FDM technique only. So FDM technique was nothing but you have PLA, or I don't know exactly whether it was ABS or PLA, added some kind of lead material reinforcement
Yes, sir. Sir, carbon fibers in
carbon
PLA, sir.
carbon fiber layering was done, and then we tested it. So if I say, for example, if I put that carbon fiber direction in one particular direction or 45-degree angle or 9-degree angle, now I have printed those, and as per ASTM I will test it. So if I have this data I can use further in a model, and that I can predict that if somebody does this way, these are the input parameters and these will be the predicted property. So that is machine learning. So one or two data will not help. If you have extensive data, then the model, more and more data you have, that model becomes mature. Like robot, we have teach type robots. So more and more extensive exposure that robot, we have more and more versatility of the robot. Similar is machine learning here. I hope this is answered.
Yes, sir. Thank you, sir.
So anywhere and everywhere you can use machine learning. I think Parth, I met you. You are from which
Yes, sir.
organization here?
Sir, I am working in Banasthali Vidyapeeth, sir. I am your former student. You have taught me engineering drawing in Gautam Buddha University, sir, in
Oh,
2011, sir.
and I think I evaluated your synopsis also.
Yes, sir. Yes,
That's
sir.
why I recollect your
Yes,
name,
sir.
Parth. You are with
Yes, sir.
scholar here. Okay, right, Parth.
Yes, sir.
All the
I am
best for your
presently
PhD.
working in Banasthali, sir, as assistant professor, sir.
Oh, very good. You're working there. Great. All
Yes,
the
sir.
best.
Thank you, sir.
Thanks for listening and answering and questioning. Any more question?
Any other participant who wish to interact with the speaker, they can unmute or write their questions in chat box. So then I will share recording and as well as detail of our expert speaker research group and Mali sir's lab which he has developed. So those who are interested, they can contact to Mali sir in MNIT by email or by phone. Those who want to start their research career in the field which we got idea in this session. Thank you, sir, for this informative session
Thank you,
where
Dr.
we
Kailas. Thank you.
came to know about the application of 3D printing in biomedical applications and a lot of work done by your team. So it's a great honor to listen you, and I will be happy to interact with you in future also. I'll be sending my research students to your lab also. So we are
Always
in,
welcome.
so it's not an end, it's in beginning, sir. We'll be giving you burden in future also, sir.
Not a problem, Dr. Kailas. You are always welcome.
Thank you, sir. Thank you. So can
So
we
thank you very much.
now?
Yeah.
Yes, sir. With your permission, now I'm ending this session, sir.
Thank you very much. All the best to everybody.
Okay.
Thank you.
Thank you, sir. Goodbye, sir.
Thank you.